For more than a decade, scientists believed our sun was going quiet. Fewer spots, the weakest maximum of the entire space age. They were wrong. A panel of NOAA and NASA scientists forecast the coming peak at 115. The sun delivered 161.39% higher and 9 months early, which means the models we built to predict our own star is doing something it was not supposed to do, and not one of the models saw it coming. Here is the thing that makes this possible. We have been counting sunspots continuously since 1755, counting every clear day for more than 2.5 centuries, by hand and then by instrument. It is one of the longest, unbroken scientific records humanity possesses. Each stretch of that record gets a number. The cycle that began in December 2019 is the 25th. We call it Solar Cycle 25. And when it began at almost nothing. The smoothed sunspot number at the start was 1.8. The sun was, for all practical purposes, blank. Now, sunspots are not really spots. They are magnetic wounds. Places where the sun's magnetic field has been squeezed so tightly that it chokes off the flow of heat rising from below, leaving a patch of surface cooler and therefore darker than everything around it. Counting them is not counting blemishes. It is counting how tangled the sun's magnetic field has become. That tangle rises and falls on a rhythm of roughly 11 years, sometimes 9, sometimes 13. Astronomers call it the Schwabe cycle, and it is the closest thing our star has to a heartbeat. The trouble is that we do not know what sets the tempo. We know the cycle exists. We know it has run for centuries. But the internal clock driving it, the mechanism deciding whether the next cycle will be violent or quiet, remains genuinely unsolved. Which is why, in the years before Cycle 25, the forecasts did not converge. They scattered. One team predicted a peak of 65, another predicted 78. NASA's own estimate was 70, with a wide margin, describing a cycle 30 to 50% weaker than the one before it. Two researchers went further and suggested the coming decades would settle into an extended, unusually quiet stretch. But other teams looked at the same star and saw the opposite. One group in China predicted a peak near 169. A team at the National Center for Atmospheric Research predicted 233. That is a spread of nearly 200 on the same star, in the same decade, using the same data. And in the middle of that disagreement sits a man whose work made all of it possible. His name is Eugene Parker. In 1958, he wrote a paper predicting that the sun does not simply sit and glow, that it constantly exhales, streaming charged particles outward in every direction, filling the entire solar system with its own atmosphere. He called it the solar wind. The idea was not initially welcomed. It described something nobody had ever seen. 4 years later, a spacecraft on its way to Venus flew straight through it. In 2018, NASA named a spacecraft after him. It was the first time the agency had ever named a mission for a living person. And bolted beneath its high-gain antenna, along with the names of more than 1 million people, they mounted a copy of that 1958 paper, the one that had been doubted, and sent it into the corona. That spacecraft is going to matter later. The first sign that something was off came almost immediately. In the first year of Cycle 25, from December 2019 through November 2020, the sun produced roughly twice as many spots per day as it had at the same stage of the previous cycle. 101% more. That could be noise. Cycles start unevenly. Years 2 and 3 settle down 7% higher, then 8% higher, close enough to normal that the forecasts still looked defensible. Then year 4 came in 41% higher, year 5 came in 71% higher. By August 2024, a single white light image of the sun taken from the observatory in Belgium showed a disk so crowded with dark regions that the daily count pushed well above 250. Large, complex active regions were crossing the face of the star, one after another, month after month, And then the peak arrived. October 2024. The 13-month smoothed sunspot number reached 161. Sit with that for a moment. The consensus panel had said 115 plus or minus 10. The realized value was 161 outside the prediction, outside the error bars, and outside them by a wide margin, 39% above the number that everyone had agreed on. It also arrived early. The panel expected the peak in mid-2025. It came in the autumn of 2024, roughly 9 months ahead of schedule. Now, a single number from a single method is never enough. So here is what makes this result solid. Independent instruments, measuring completely different things, agree. A pair of solar sensors in Earth orbit, tracking the sun's output in specific narrow bands, recorded their own peaks on the 1st of October and the 29th of September, 2024. A separate set of instruments aboard the GOES weather satellites recorded a peak on the 1st of October as well. And when the raw daily sunspot counts are smoothed using the same window, they peak on the 20th of October. 3 independent measurement systems, roughly 19 to 21 days apart, all converging on the same month. That is what confirmation looks like. Not one team announcing a result, but several instruments that have no reason to agree arriving at the same answer anyway. The scale of the overshoot becomes clearer when you stop looking at the peak and start counting days. Measured to the same point in each cycle, cycle 25 spent 947 days with a sunspot count above 100. The previous cycle managed 622. Above 200 spots, cycle 25, 98 days. The previous cycle, 3. Above 250, 16 days versus 0. Above 275, 5 days versus 0. The previous cycle never once reached those levels. This one reached them repeatedly. Averaged across the whole thing, the sun has been producing 31% more spots per day than it did during the same stretch of the last cycle. So the question stops being whether the forecasts were wrong. They were, and everyone involved has said so plainly. The question becomes what the sun is actually doing that our models did not contain. To understand the miss, you have to understand the machine. The sun is not a solid object. It is a ball of ionized gas held together by its own gravity, and it does not rotate the way a planet rotates. Different parts of it turn at different speeds. The equator completes a rotation in about 26 days. The polar regions take about 33. That difference is everything. The sun's magnetic field is locked into its plasma. The two cannot slide past one another. The field is, in a real sense, frozen into the material. So when the equator laps the poles, over and over, year after year, the field lines cannot stay straight. They get dragged forward at the middle and left behind at the top and bottom. They wind up. Over roughly 5 to 6 years, an orderly magnetic field shaped something like a bar magnet is twisted into something else entirely wrapped around the star, like thread around a spool. And a wound field is an unstable field. Lines cross, lines pinch, lines snap. Where they snap, energy escapes. That is a solar flare, that is a coronal mass ejection, that is a sunspot. Then, at the point of maximum tangle, something remarkable happens. The whole thing turns over. North becomes south. The sun reverses its own magnetic polarity and begins winding itself up again in the opposite direction. For cycle 25, that reversal happened in 2023. Now here is where the standard picture starts to break. Everyone assumes that when a star is covered in dark spots, it must be dimmer. Dark patches on a bright surface should mean less light. It is intuitive, and it is wrong. The sun is measurably brighter at solar maximum. The reason is that sunspots are only half the story. Alongside every dark spot, the same magnetic activity produces bright regions called faculae, glowing areas that outshine the ordinary surface around them. So the sun's total output is not set by darkness or brightness alone. It is set by the balance between them. Facular brightening on one side of the scale, sunspot darkening on the other. At maximum, brightening wins. And this is where cycle 25 stops being merely energetic and starts being genuinely unusual. Compared with the peak of the previous cycle, the brightening from facula in 2024 was 57% higher. The darkening from sunspots was 47% higher. Both went up, but they did not go up together. The ratio of brightening to darkening at the peak of cycle 25 is higher than at the peak of the 4 cycles before it. Something about this cycle is preferentially building bright structures rather than dark ones. The sun's magnetic field is expressing itself differently than it did in living memory. The consequence shows up in total output. The sun's average energy delivery to a square meter at Earth's distance sits at about 1,361 watts. Across a full cycle, that figure moves by only about 1 watt. It is a tiny variation small enough that on its own, it does not meaningfully drive Earth's climate. For comparison, the warming pressure added by human greenhouse gases is around 3 watts per square meter, and unlike the solar cycle, it does not swing back the other way. But in 2024, that annual value did something notable. It rose above the peak of the previous cycle and above the peak of the 5 cycles before that as well. Not the highest ever recorded, but the highest in the entire era of direct space-based measurement. And in the ultraviolet, where the effect is amplified, the difference is stark. In the band containing a particular magnesium feature, the most variable wavelength region we can reliably monitor, the previous cycle varied by about 3.8%. This cycle varied by 5.8%. There is a 100-year rhythm buried in the sunspot record, slower than the 11-year beat and much harder to see. Set that aside for now. If a cycle runs stronger than forecast, you expect more storms. That happened. But some of what happened does not fit neatly into more. Start with May 2024. An active region on the solar disk released the strongest flare of the cycle up to that point, a magnitude 8.7 event in the X class, the highest classification we use. What followed was the most severe solar storm to strike Earth in 20 years. Aurorae appeared at latitudes where aurorae do not appear. In Belgium, people photographed colored light in the sky over their own cities. Now, a storm of that magnitude is uncommon but not unheard of. Statistically, one arrives roughly every 12.5 years, but the intensity was not the anomaly. The anomaly was the duration. That storm lasted so long that, by the historical statistics, an event of that length is expected roughly once every 41 years. Then, a few days later, a flare classified at magnitude 12 erupted, and it was not pointed at Earth, it was pointed at Mars. X-rays and gamma rays struck the planet, followed by a coronal mass ejection. And then the pattern simply continued. Another major storm in October 2024. Another in June 2025. Another in January 2025. On the 1st of October 2024, a flare of magnitude 7.1. 2 days later, magnitude 9. In November 2025, a region produced a flare of magnitude 5.16, the strongest of that year and the 6th largest of the entire cycle, launching a coronal mass ejection at 1950 kilometers per second, fast enough to trigger a rare high-level geomagnetic watch. There is a strange upside to this. Each of these storms was sampled with the full range of instruments now in orbit. We have never had this many eyes on the sun during a period this active. Every one of these events makes space weather forecasting slightly less blind. But some anomalies had nothing to do with the sun at all. In early 2023, one of the satellites carrying our most stable, long-term solar instrument, a spectrometer that has been in orbit for more than 20 years, and provides the highest precision ultraviolet record we have began running. Out of fuel, it could no longer perform the maneuvers that held its orbit steady. As a result, the angle at which sunlight fell on its calibration surface began to drift outside the range it was designed and tested for. In late 2023, and again from October through December 2024, portions of the detector recorded deviations of up to -4%. Read that again, because the timing is uncomfortable. The instrument measuring the sun's peak began misbehaving during the peak. The team did not discard the affected data. They compared the drifting detector rows against the rows that held steady, traced the pattern of the error across wavelength, and built a correction from the instrument's own healthy segments. They chose to correct rather than delete, because deleting rows would have introduced its own bias. That is what scientific honesty looks like from the inside, not a clean measurement. A flawed measurement, publicly identified, publicly repaired, and published with the repair described in detail. Then there is what happened at the poles. For essentially all of history, every telescope and every spacecraft has looked at the sun from roughly the same place, the flat plane in which the planets orbit. That plane is tilted only about 7 degrees from the sun's equator. 7 degrees is not enough. From that angle, the sun's poles are permanently foreshortened, glimpsed edge-on, never properly seen. One mission flew over them between 1990 and 2009. It carried instruments to measure fields and particles. It did not carry a camera. So in February 2025, the European Solar Orbiter spacecraft used a swing past Venus to throw itself out of the planetary plane entirely. By mid-March, it was looking at the sun from roughly 15 degrees below the equator, and on the 22nd of March, it reached about 17. For the first time, we photographed the bottom of our own star. The scientist leading the magnetic imaging team described the poles beforehand in blunt terms, literally unknown territory. Nobody knew what the images would show. What they showed was a mess. Earth's magnetic field has a clear north and a clear south. The sun's south pole, imaged at the height of its activity, showed both polarities scattered together in a fragmented patchwork, small regions of opposite magnetic sign sitting side by side with no clean structure at all. Models had predicted this. No one had ever confirmed it. And the timing was, by the team's own account, fortunate. The spacecraft arrived at high latitude precisely during the reversal, catching the poles mid-collapse rather than in their settled state. There is one more anomaly, and it comes from the spacecraft carrying Eugene Parker's paper. In December 2022, at a distance of roughly 16 solar radii, the Parker Solar Probe flew through a region where the sun's magnetic field was tearing and reconnecting. Reconnection is the process that powers flares crossed field lines, snapping and violently rearranging, flinging particles outward. The probe measured protons accelerated to energies around 400,000 electron volts. The available magnetic energy in that region per particle was around 1,000 electron volts. The particles came out with roughly 1,000 times more energy than the local magnetic field appeared to contain. And when the team examined which particles gained what, they found something the models explicitly did not predict. Protons and heavier ions were supposed to behave identically. They did not. The heavy ions emerged in tight, beam-like streams. The protons emerged scattered and dispersed, spread across a much wider range of directions, with a distinctly different energy distribution. The current explanation is that the protons, being far more numerous, generate waves that then scatter the protons themselves, the particles interfering with their own acceleration. But the existing simulations do not reproduce this. The paper's own conclusion is direct. The models will have to change. None of this means the sun is behaving in a way that has never happened before. That distinction matters, and it is worth being precise about it. Cycle 25 peaked at 161. The cycle before it peaked, at 116.4, in April 2014, the weakest maximum of the entire space age. The cycle before that peaked at 180.3 in November 2001. So this cycle is not a record. It is stronger than the last one and weaker than the one before. Placed in the 2.5-century record, it is a solidly active cycle, not an extraordinary one. That, in a sense, is the point. Because the expectation was not that cycle 25 would be ordinary. The expectation, held across much of the field for more than a decade, was that it would be exceptionally quiet, the beginning of a long decline. The reasoning was sound. The minimum in 2008 and 2009 was unusually deep and unusually long. Cycle 24 that followed was the weakest in the space era. Historically, when the sun goes quiet like that and stays quiet, it can stay quiet for a very long time. We have a name for the extreme version. Between 1645 and 1770 years, sunspots very nearly stopped appearing. That period is called the Maunder minimum. A milder version occurred around 1805, the Dalton minimum. So when researchers looked at 2009 and saw a sun going silent, the natural question was whether we were watching the opening of another one. Multiple studies concluded that activity would likely fall substantially for the next 90 years. One influential 2006 model, using long-period oscillations layered on top of the 11-year beat, predicted that cycle 24 would peak at just 42. Cycle 24 peaked at 116. That same expectation of decline reached the climate modeling community. When scenarios were assembled for international climate simulations, one adopted scenario had cycle 25 matching the weak cycle 24, followed by 6 consecutive cycles of steady decline. The first step of that projection has already failed. There was an earlier signal too, and it was public. In June 2023, the monthly sunspot number reached 163.4, the highest figure in more than 2 decades since September 2002. At that point, cycle 25 was only 3.5 years old. The sun was, well ahead of schedule, already outrunning the forecast. So we return to the rhythm mentioned earlier. Underneath the 11-year cycle, the sunspot record contains a slower oscillation with a period of roughly 100 years. It is called the Gleisberg cycle, and it does not create solar activity. It modulates it, raising and lowering the ceiling that each 11-year cycle is allowed to reach. In 2014, 2 researchers proposed a reinterpretation of the quiet decade. The deep minimum of 2008 and 2009, they argued, was not the beginning of a new Maunder-like silence at all. It was simply the trough of the 100-year cycle. The previous troughs on that reading fell between 1900 and 1910, and between 1810 and 1830. If that is right, then cycle 24 was not weak because the sun is shutting down. Cycle 24 was weak because it happened to fall at the bottom of a longer wave, and a wave that reaches a bottom does not stay there. This is a hypothesis. It is important to label it as one, but it is a hypothesis that made a prediction, and the prediction has now been tested. If the deep minimum was a Gleisberg trough, the next cycle should come in stronger than the last. It did. The projections that follow from that model are the part worth watching. They suggest that solar maxima may continue rising for the next 3 cycles, the exact opposite of the declining scenario written into climate projections. Because the sun's polar field reversed in 2023, the 2024 values are almost certainly the true peak of this cycle, and output should now decline. The next minimum is expected around 2029. The official forecasting center places the start of cycle 26 somewhere between January 2029 and December 2032, and states plainly that it does not yet produce a prediction for that cycle. If the pattern holds, the next maximum falls around 235, and it may be higher than the one we just watched. That word "if" is doing enormous work. The researchers who published these projections say so themselves. They describe them as conceptual estimates built from simple statistical representations of two overlapping rhythms. They state that continued observation is essential to determine whether a new Gleisberg cycle is genuinely underway, and if it is, whether it will resemble the last one or behave differently. Which brings us to the uncomfortable part. The instrument that produced our most stable ultraviolet record, the one that ran out of fuel, drifted out of calibration, and was carefully repaired, is ending. Its spacecraft is scheduled to be decommissioned. Other instruments will pick up the record, and the teams have already named which ones. But a 20-year continuous measurement made by a single unchanged sensor is not a thing you can simply replace. Every handoff between instruments introduces uncertainty exactly where you least want it, in the long-term trend. Meanwhile, out beyond the plane of the planets, the solar orbiter continues to climb. Its plan calls for another Venus encounter at the end of 2025 that would tilt its path further, and by 2029, higher still, until it looks down on the Sun's poles from around 33 degrees. And the Parker Solar Probe, having flown closer to the Sun than anything humans have ever built, closer than 6.1 million kilometers from the surface, at a speed of 191 kilometers per second, continues its loops. Its shield is a slab of carbon composite 2.3 meters across and 11 centimeters thick, weighing 73 kilograms, holding back a wall of light 475 times more intense than anything Earth receives, and keeping the instruments behind it at roughly the temperature of a warm afternoon. Radio takes 8 minutes to reach it. It cannot be saved by anyone. It watches for the first sliver of direct sunlight at the edge of its own shadow and corrects itself, alone. Eventually, its fuel will run out. The plan is to turn it deliberately and let the instruments face the Sun unshielded for the first and last time. They will be destroyed in moments. The shield will survive. It is expected to keep orbiting the Sun for millions of years. So where does that leave us? We know, as fact, that solar cycle 25 peaked in October 2024 at a smoothed sunspot number of 161. We know it exceeded the international consensus forecast by 39% and arrived early. We know that multiple independent instruments confirm it. We know the Sun's total output in 2024 rose above the peak of the previous 5 cycles. We know the balance between bright regions and dark regions shifted in a way that has not been seen in the 4 cycles before this one. We know that the reversal of the Sun's magnetic field in 2023 was photographed at the South Pole for the first time in history, and that what we found there was not a pole in any ordinary sense, but a scattered patchwork of opposing polarities, still in the middle of turning over. We know that particles near the Sun are being accelerated to energies 1,000 times beyond what the local field should be able to supply, and that they are not all being accelerated the same way, and that our simulations do not yet reproduce this. What we do not know is why any of it is happening. We do not know what sets the length of the cycle. We do not know what determines its strength. We do not know whether the 100-year rhythm is a real physical mechanism or a pattern we have fitted onto a record that is only 25 cycles long. We cannot say with confidence what the next maximum will look like, and the agencies responsible for saying so have declined to say. We built a forecast and the Sun ignored it. Then, we built better instruments and pointed them at the thing that had embarrassed us, and the instruments came back with measurements that broke the models we had used to interpret them. That is not a failure. That is the only way this has ever worked. For 400 years we have watched this star. We have counted its spots by hand since before the founding of most modern nations. We have flown through its atmosphere and photographed its hidden pole and measured its light to within a fraction of a percent. And what all of that effort has finally revealed is not an answer. It is the precise shape of our own ignorance, mapped in detail, published in full, and larger than anyone expected. The Sun has been doing this for 4.5 billion years. We have been paying close attention for about 70. We are not watching a star behave strangely. We are watching a star behave normally for the first time, with our eyes finally open and discovering that we never knew what normal was.